Stanford University.
All right, I was going to talk about the second law of thermodynamics, which I don't remember if I talked about it all or not. Did we? Did we talk about the second law? But this is, remind me, did we talk about the second law? And no.
Yeah, we could have gone there or the black hole entropy, I think.
All right, so let's talk about the second law of thermodynamics. It's a very tricky law. On the one hand, it says that a certain something associated with the system always increases. On the other hand, Newton's laws of motion are reversible. Any trajectory can be reversed, and there's another possible trajectory where just everything runs backward, where the movie runs backward. What do you have to do? Supposing I pick a solution of Newton's equations. Again, let's take x and p. That's a phase space in now a very simple system with one coordinate and one momentum. What is the trajectory of a system in the phase space? Supposing we start over here at some instant of time and follow the system, and it goes to here. Right? That's a particular trajectory of the system, early times, late times, and it goes this way. There is another trajectory of the system, which is the time reversed trajectory. Is it just a trajectory from here to here? Not quite. Not quite. And the reason is that in order to reverse the trajectory, you have to reverse the velocity. So a trajectory which goes from here to here, in order to find the inverse trajectory, the time reverse of it, you have to start with the object going in the opposite velocity. So that means you have to reflect all velocities, which mean reflect all momenta. There's another trajectory, let's see if I can draw this, which looks like that, which is just a reflection. And the reflection just means that at every point along the trajectory, it's running with the opposite velocity. You know, if you see a movie and you see a car going with a certain velocity and you run the movie backward, the car is going with the opposite velocity. But other than the fact that the velocity is reversed, Newton's equations are completely reversible. And so, for example, if there's a trajectory of a many-particle system where the particles start off in the corner of the room over here and then move to fill up the entire system and come to thermal equilibrium, and after a time of order a few seconds or something, well, it's probably longer than that, but after a time of a few hours, the molecules distribute themselves in thermal equilibrium. Then if we could get into that system and reverse the motion of every molecule, in other words, change the sign of its velocity and run it, it would, according to Newton's equations, just run backward and all the molecules go back into the corner. Now, nobody ever sees that, and it seems to violate, it does violate, the second law of thermodynamics. So what's going on? How can it be that Newton's equations are time reversible and the second law of thermodynamics is a complete one-way job? It tells you that systems always go in one direction and never in the other direction. This was an extremely confusing point that was sorted out relatively late, in the last 30 years or so. Boltzmann had much of the right ideas, but he didn't quite clinch it, and it took some time. The key is the idea of chaos. The key is the idea of chaos. So let's talk, and of course, the answer is that not that this can't happen and the system go to some very unlikely state. It's just that it's unlikely for the system to go to an unlikely state. So a sudden reversal of entropy of a system going from a maximally disordered state in which all the particles are in random positions filled up this volume here to a highly ordered state where all the molecules are in the same corner of the room, That's not impossible. It's just very unlikely. So we have to understand better. If we want to understand the second law of thermodynamics, we have to understand the way systems move in phase space. Because that is what it's all about, how systems evolve in phase space. Now again, phase space is multidimensional, and I will have to represent it just necessarily because we don't have enough dimensions on the blackboard. We will have to represent it as just two-dimensional, p and x, well, x and p. Now, there is a rule in phase space about the way systems evolve. If you start with a lump, let's start with a lump in phase space. There's a lump, a nice round lump. It's not particularly round, but a nice round lump in phase space. What does that mean? That means all of the possible starting points in this lump here, and evolve each one of them. The lump evolves into some other shape. Follow each point in the phase space with time. It evolves into another shape. What's the rule about the evolution of the lump in phase space? Equal volume. Equal volume. Now, if you have a lump, now what a lump means is a probability distribution. And let's just take it for simplicity to be the probability distribution which is 0 on the outside of the lump and not 1, but constant on the inside of the lump. All right, so it's a probability distribution which tells you no more or no less than the system is in the lump. And the lump evolves, and after a time, all you know is that the system is someplace in the displaced or evolved lump. What is the entropy of, this is a probability distribution. Okay, this is a probability distribution, and so it has an entropy associated with it. The entropy is logarithm of the number of states that are in the probability distribution. If the probability distribution is flat over some set of states, then the probability is simply logarithm of the number. But wait a minute, we can't quite say that when the states are continuous like this. The number of states in there is quite infinite, continuously infinite. And so in classical physics, again, we divide the phase space into little cells, and the right statement is that the entropy is proportional to the volume, to the logarithm of the volume. Did I say the logarithm of the volume in phase space? That's the classical analog of the logarithm of the number of states, the logarithm of the volume. And the volume is conserved as the system moves, So as time goes on, no matter what the system does, the lump in phase space has exactly the same volume that it started with. The implication is that the entropy, since it's just the logarithm of the volume in phase space, stays the same. But that's not consistent with what we know about the way systems behave. Entropy increases. So we can state the puzzle either through the puzzle of reversibility, that what goes one way can go the other way. That seems to be inconsistent with the law of increase of entropy. But we can state it another way through the principle that the volume in phase space is constant with time. And that says that the volume's constant, the logarithm of the volume is constant, and the entropy simply can't change. Whatever the probability distribution is, the entropy can't change. So what is the meaning of the second law of thermodynamics? And to understand that, we have to first have an idea of what chaos is. Chaos, to illustrate chaos, my favorite example is a billiard table. But let's make it an idealized, frictionless billiard table with no pockets, please. No holes in the billiard. Everybody's played three-cushion billiards, right? You know that there are billiard tables that don't have holes in them. Right, so but we'll put a whole bunch of billiard balls in. We have all the numbered balls, 1 through 15, plus the cue ball. The cue ball is over here. 8 ball over here, 7 ball over here, and the cue ball. All right, now they're all perfectly at rest. It's a completely frictionless billiard table. The cushions are perfectly reflecting. They're not made of rubber. They're made of the perfectly reflecting cushions. And so it's an idealized, dissipationless, this is the game of dissipationless billiards. Right? And we shoot the cue ball at a very definite angle, at a very definite velocity, extremely precise. The laws of mechanics tell us that the system will follow in a deterministic way a trajectory which is infinitely predictable if we know the initial condition with perfect exactitude. All right? But what happens if we make a tiny mistake in the direction that we shoot the billiard ball in? Well, a tiny mistake here, instead of sending this billiard ball off this way, we'll send it off at a slightly different angle. It'll reflect. This one reflects over here. And as you can kind of see, now this one might hit this ball, where this one not hit that ball. And boy, then really the evolution after that point is entirely different. Okay? Errors or small deviations in the initial conditions build up exponentially for most systems. Now there are special systems where this doesn't happen. Let's just take one billiard ball on a square billiard table. Then the motion, or even better, a one-dimensional billiard. One-dimensional billiard, and we shoot the ball this way with a certain velocity. It just goes back and forth, and there's nothing to build up exponentially. All right? This is quite stable. But most systems, almost all systems, are chaotic. Chaotic means exceedingly sensitive to the initial conditions in such a way that two initial conditions, which are close together in phase space, will start exponentially deviating from each other. All right, so if we take 2 points in phase space and we follow them, they're very close. We follow them, they exponentially depart from each other. So the distance between these 2 points, let's say the initial separation was just epsilon. The initial separation is epsilon. Then after a time, the separation will be epsilon times e to a number, I'll call it delta, times t. That delta depends on the system. It may even depend on where you are in the phase space, but in general, it's a number that exponentially increases the separation between phase points. If epsilon is exactly 0 to begin with, the separation after time delta t is also 0. But if epsilon is a small, very small number, but non-zero, then in not too long a time, depending on this delta here, the separation will become large. Once it becomes large, they go off on their own way, and the trajectories don't resemble each other. This number here is called an exponent, or it's called a Lyapunov exponent. Lyapunov. Oh boy. UN, I think. Yup. The Lyapunov exponent. And it just represents the degree of instability. It's generally positive, and away you go. Okay, now how can this be consistent with the statement that the phase space volume stays fixed? If all points sort of deviate from each other exponentially, how is it that the phase space volume doesn't grow? Okay, how come it doesn't grow? What happens is a little bit different. It's not that it grows. It separates into a kind of fractal. So let me try to draw, roughly speaking, what happens in a chaotic system. You start with a phase space blob, which is nice and regular. And you evolve. Well, it starts to get a more complicated shape, and it starts to grow tentacles or filaments. It forms a filamentary structure where the filaments get kind of narrow, but the total volume doesn't change. You go a little further, and the filaments start to break up into very narrow, lots of them. Oh, God, I hesitate to try to draw it. And it becomes a kind of very complicated fractal with exactly the same volume as it started with, but with a shape which sort of spreads out its tentacles. So it's like a piece of cotton wool, you know, a large piece of cotton. Yeah.
If it's connected, it stays connected.
If it's connected, it stays connected. If it's connected, it stays connected. Yeah. The topology does not change. If it's simply connected, it stays simply connected. If it's multiply connected, it stays multiply connected. But no matter how you start in a chaotic system, it starts to grow tentacles, and the tentacles cause the phase space blob to sort of spread all over the place, and not only spread all over the place, but in a certain sense get very dense. Now, its volume does not increase. So it's like a piece of great big fuzzy cotton that could fill this whole room, even though its volume, if you were to squeeze it down so that you were actually looking at the volume of actual material, might be small. Okay? That's the way things evolve in phase space. Okay, yeah.
What happens when it gets thinner than the Planck line?
Well, okay, then we have to deal with quantum mechanics. And incidentally, the Planck unit, Planck's constant, forget Planck length. We're not getting into quantum gravity at the moment, so forget Planck length. But Planck, I think you meant Planck's constant. Yeah. Okay, Planck's constant is a unit of area, not a unit of length. Planck's constant is a unit of momentum times length. So it's a unit of area in the phase space. Okay? So it's a proper question, but at the moment we're doing purely classical physics, where Planck's length or Planck's constant corresponds to an infinitely small volume or infinitely small area in phase space. So there's no, in classical physics, you never get to the Planck size. Now, to do quantum mechanics, you have to do quantum mechanics, and there is a version of this in quantum mechanics, but this is the classical version. Okay, so the phase space volume gets very complicated, but without changing its volume in phase space. On the other hand, we should take into account, and we should always take into account, that in general, our ability to distinguish points in phase space is limited. Right? Not just limited because the bathtub full of hot water just has a given temperature and not much else, but even if we had microscopes that could see every particle, there still would be a limitation, or we should assume that there is a limitation on our ability to resolve those points. Whatever that ability is, let's represent it by a small little cell, not a cell, a small little blob in phase space, which is itself much smaller than the original blob. And let's just say every point in this phase space is replaced by a blob of that big. In other words, we can't distinguish one point in the blob, one point in the mini blob from another, and so we just fill it up like that. All right, we're going to, since these blobs are a little bit coarse-grained, they might actually make the volume, if we replace every point on the inside by one of these small blobs, it will increase the volume a little bit. Just because each point on the boundary here will be spread out a little bit. But on the whole, that won't be much of an effect as long as the blob is a nice regular blob like this. Okay? So if you start with a nice regular blob, the volume in phase of the coarse grain, this is called coarse graining the phase space, means looking at the phase space as a collection of coarse-grained little areas like this. Coarse graining, a nice smooth configuration in phase space, doesn't change its volume significantly. But as this starts to blossom more and more tentacles, you can see what starts to happen. Let me try to draw this in a way which makes clear what begins to happen. Okay, so eventually we get to a configuration where it just bristles out structure, very, very thin filaments in every direction in the phase space. And now let's coarse grain the evolved blob. If I coarse grain the evolved blob, well, first of all, it gets big. It gets big not because its volume increases, but because it just grows enormously long tentacles of very, very thin regions of phase space. And
Coarse blobs are way too big.
yeah, the coarse graining blobs are too big to distinguish between the different branches of this fractal. And so what happens when you coarse grain it is it gets much bigger. Just like a large cotton ball, if we replaced each fiber of the cotton by a thicker fiber, then the volume of the cotton would be much bigger than the original starting volume where it was compressed down to something small. Okay. In fact, it will get about as big as this whole structure, this whole multi-tentacled structure. It'll all get sort of filled in by the coarse graining. It really doesn't matter very much how much coarse graining you do. In other words, what the volume of these coarse-grained little cells is. Eventually, this thing gets so fractalized. I don't know what the right word. There must be a verb that goes with being fractalized. All right, I invent the verb. Fractalized. It becomes so fractalized that when it's coarse-grained, it will always grow. So now we have to distinguish between the fine-grained entropy and the coarse-grained entropy. The fine-grained entropy is the exact logarithm of the volume of the phase space, keeping track of the infinite fine-grained structure of phase space. That never increases. That is frozen by Liouville's theorem. On the other hand, this more physically useful coarse-grained phase space, the coarse-grained phase space where the distinctions between very, very close points are blurred over, that volume does grow. So the logarithm of the coarse-grained volume increases. It's the coarse-grained volume that defines the conventional entropy of thermodynamics. And you see, there is really not a contradiction. Now let's go back. Let's suppose this system evolves into this system over here, or much more complicated than this system over here. Let's just complicate it by putting a lot more structure into it. All this fibrous. All right, now, what about when we go backward? Let's come back to the question of running the system backward. Okay. This might represent all the particles off in the corner of a room. This might represent what happens to those particles when they fill up the volume of space. Okay? Let's run the system backward. Here's the rule. Here's what we know. If we start on any one of the tentacles, on any one of the fibers, right, we will trace back to here. But on the other hand, if we start nearby one of the fibers have gotten so thin that this chaotic behavior, the Lyapunov exponent here, instead, whereas this point over here might have traced back to here, this point neighboring to it will trace back for a while and then go off to some wildly different place. The lesson is that yes, if you did literally reverse every particle exactly After the particles had left the corner of the room, they would go back to the corner. But make the tiniest mistake in one particle, after a couple of collisions, the system will have essentially lost memory of the fact that it was just a time reverse of this very unlikely state that you started with. And what will it do? It'll just continue to fill up the room with particles. Okay? So yes, it is possible to reverse the law of entropy, but the likelihood is extremely small. This whole blob of phase space here, this whole coarse-grained blob of phase space is very big. Most of the points look a lot like each other, and it's only a terribly tiny fraction of it that traces back to this extremely unlikely state. Most of it leads to configurations which are even bigger and spread out even larger. That's the second law. That's the nature of the second law.
The 2 points you're talking about that are close to each other, they're both within one of the filaments?
No. One of them's outside the filament and the other's inside the filament. Right. If they were both inside the filament, they would both lead back. They might lead back to different points here. All right. So if they were both in the filament or in rather distant pieces of the filament, they would lead back to the same blob here. But if one of them, and remember, these filaments are very fine now, extremely fine, and so even if one point is just a tiny, minute distance outside the filament, with time, the exponential growth in the error will lead you to some wildly different point in the phase space. Most of those points that this filamentary, this coarse-grained filament will lead to will be of yet larger entropy. In other words, if you follow them either backward or forward, it doesn't matter. Let's follow backward. If you follow backward, this point will go to here. This point will go to here. But this point over here will go out to here. So if you follow all the points in this filamentary structure backward, you will not get most of these points back into this tiny little volume here of phase space. They will go off and make yet an even more complicated filamentary structure. The second law goes,
Sorry, would you say that if you actually did the full integral of that whole filament spider web, that you would always get the original volume, but that really you can't?
I'm not sure what integral you want to do, but...
Integral over the whole phase space. The implication of integrating over phase space is that you can go to every... Integrating, you can go to every point of phase space and retrace it back exactly. Whereas if you're summing, then you're sort of coarse-graining.
Yeah, when you sum, you're effectively coarse-graining the phase space.
So the amount of coarse graining is related to the sizes of your delta X?
It is, but it hardly matters. The answer is it hardly matters how much coarse graining you do. This filamentary structure grows so quickly and gets so dense that it doesn't matter very much what the size of the coarse graining is. It'll define a blob whose size is pretty much independent of the size of the coarse graining. Just because these coarse-grained fiber, these fine-grained fibers here get very, very close together, and it hardly matters what your coarse graining size is. The result of coarse graining will be to fill up the whole volume of this branched structure. Yeah.
In that picture of the guy jumping off the diving board into the pool.
Yes.
Okay. If he ends up going back onto the diving board, being pushed out by the molecules of the water in the pool.
Yeah.
Does that violate any basic law of physics?
No, it violates no basic law of physics other than it's extremely unlikely because just one little molecular accident of the wrong kind will completely undo. So one little molecular accident means a slight shift in the initial conditions will simply lead him plop back into the water.
What I like about the billiard ball one, and I think somebody calculated that Jupiter could have the gravitational effect of Jupiter could change the path of phase space at some point. And that's how.
Wait, say it again?
that the gravity of the people standing around the pool table can change
To change the orbits of
the trajectory.
the trajectory of.
Of the billiard balls after a while.
Oh, sure. Yeah, just a butterfly waving its wings 1,000 miles away can. Can do it.
But what other question? What about I've heard that the second law of thermodynamics is the fact that it obtains in this universe is a function of the initial conditions.
Yes. Yeah, no. Yeah, it does. If you follow this blob forward, it'll increase its volume. Follow it backward in detail from each point within the fibrous structure, and the volume will decrease. But coarse grain it, now you're going backward. You're going backward in time, but following the system backward in time, it'll still increase the volume of phase space when you go backward. So the second law of thermodynamics would work in both directions. Start with an initial configuration, run it forward, run it backward. The most likely thing to happen is that entropy will increase. So then what is the meaning of the fact that entropy increases in one direction and not the other? The meaning of it is that the world started with a very low entropy for reasons that have to do with cosmology and that we don't completely know. For some reason, the world started in a state of very low entropy. Why? Nobody knows, because nobody knows that much about the initial state of the universe and why it was started. But what we do know is that the entropy was very low. That means we started out in a very tiny blob of the phase space. If we ran it backward, that blob would expand. If we run it forward, that blob would expand. But the fact is, cosmologically, we know that the universe started in a very ordered, small volume of phase space. So the second law of thermodynamics also entails something about initial conditions, that the universe didn't start in a random configuration. It started in the analog of all the molecules off in the corner of the room. And then they spread out. That's not exactly that. That, of course, is just an analogy. So, yes, the meaning of the second law of thermodynamics is, among other things, that the initial conditions were a configuration of very low entropy, analogous to all of the molecules in the room being in the corner. Yeah.
Yeah, if this is all predicated on the idea of this heat bath,
Well, actually not. Actually not. No, not really. No, this is not predicated. This is just predicated on the idea of chaos. This does not mean the system comes to thermal equilibrium. That's not the implication of this. It just means that you spread out and lose memory of where you started. It doesn't say that the system's energy levels are populated with certain probabilities. Okay? That's a separate story. Right. Yeah.
So is there a physical meaning to the coarse graining? It's a statement about what we can observe.
What we can distinguish. Yeah, I think it really does correspond to a. But the main point is that the degree of coarse graining is not very important, because eventually, no matter how small a coarse graining is, no matter how small these coarse grain volumes are, in not too long a time, these branches will get within that, will get closer together than that volume. The smaller we make it, the longer the time it will take for the branches to get that close together. But it's not, it doesn't depend very much on the nature of the coarse graining. And so pretty much independently of the detailed numbers of the coarse graining, just wait not too long, and the coarse graining will fill up the whole volume. And of course, there is a degree of fine graining or coarse graining, which is so precise that it will not get filled in. But then just wait a little longer and it will get filled in.
Even beyond the Planck scale?
Look, this is classical physics. If we want to do quantum mechanics, we have to do quantum mechanics. So we have to get into what quantum chaos means, and we have to get into what that's already a separate subject. So this is classical physics. No.
So there's a relationship between the size of the coarse grating and the amount of time it takes for the system to become totally...
That's for the amount of time for, yeah. Yeah. But it's not very sensitive.
Okay, but can that, is it insensitive enough that it can be mapped onto the physical world, saying this degree of coarse rating?
You could.
Over,
You could imagine doing that.
It may take 500 trillion years, in which case it...
Remember, exponentials get big very fast, right? So if this Lyapunov coefficient here is not very small, what corresponds to what here? This distance between neighboring points, which we might think of as the coarse graining, is this epsilon here. How far apart they get from each other is epsilon e to the delta t. So 2 points which are close will get far very quickly, and that means that this branching structure grows very fast. It grows very, very fast, exponentially fast. And yes, it's true that given a time scale, given a time, 1,000 years, I can prescribe the coarse graining to be fine-grained enough so that your coarse graining will not fill up the fractal structure here, will not, what's the right words, smush it out, okay? But on the other hand, given a degree of coarse graining, as a general rule, very, very quickly that coarse graining will be sufficient to smush the phase space.
Is the coarse grating density constant after a while, or is there a possibility?
Yeah, that's right. It becomes constant after a while. Right. Up to a point. Energy is conserved. Okay. So you cannot fill up the phase space if you start with the phase space blob being concentrated at some energy. All right, so what does it really look like? What it really looks like is in phase space there are surfaces of given energy. There's a surface of a given energy in the phase space. Really, this whole discussion should take place on the surface. So starting on the surface with a blob, the surface, we will not get off the surface, that's just energy conservation. But on the surface, the blob will begin to do this fractalating behavior. So apart from the conservation law of energy, after a while, this thing will really cover the phase space very uniformly. With this very, very intricate, fine threads of...
Is there something about information that you can say about this? So as time goes by, do you lose information sort of?
Well, you lose information not because some fundamental law is not predictive, but because of the fine graining. So information now, when you speak about information, you have to decide whether you're talking about fine-grained information or coarse-grained information. Fine-grained information, you never lose. Coarse-grained information, yes, you do lose it, and you lose it in just this way. So that distinction has to be made, and always has to be made.
Question. How come after 13.7 billion years, that little blob hasn't smeared itself over everything, and we're still structured here?
Well, okay, so the time scale, 13.7 billion years is not long enough, that's all. What is the right time scale? The right time scale is probably about 40 billion years, more like 100 billion years.
But it's exponential. This divergence is exponential.
The universe is very big. You start on all the molecules in the corner of the room. If the room is big enough, it will take a long time for them to fill up the room. But it won't take a long time for the entropy to start to increase. This tentacle structure here still hasn't grown to fill up the whole phase space. So how big is the phase space? The phase space is very big, and it takes a long time to get filled up. But still, the entropy starts increasing long before this thing fills up the whole phase space.
In a practical way, a dendritic growth.
Is what?
Dendritic
growth, yeah.
Is a fractal structure.
Yeah. Yeah, it's similar to that. It's quite similar to that. Right. Right. Yeah. But it's not just a fractal, but it's a space-filling fractal. A space-filling fractal which really doesn't fill the fine-grained space, but fills the coarse-grained space. Yeah. And it's not so easy to do that. Well, it's not so easy to picture it, but that's roughly what happens.
You've emphasized the initial conditions as being the
Well,
thing
somebody
we don't
mentioned
know
it.
exactly.
Say it again?
You've emphasized the initial conditions as being the thing we don't know exactly, but we never know the Hamiltonian exactly.
Right. That's another point. Yeah. If after we started, let's say we started here and we got to here, and now we want to time reverse it, but we're going to time reverse it with a slightly different Hamiltonian. Doesn't go back to here. It does essentially the same thing as what would happen if you displace the point a little bit. So yeah, a slight change in the laws of physics could completely undo the ability to reverse the. Right.
Wouldn't this coarse graining result in a violation of the prime conservation law of information?
No, coarse graining. Well.
So the information is destroyed if it's coarse graining. To a certain degree.
Yeah, information is destroyed if it's coarse-grained.
That's not a violation
of the conservation of information. No, the conservation of information is the theorem that says that the fine-grained entropy never increases. Right. So that's the big distinction: fine-grained versus coarse-grained. The very, very precise equations of mechanics say that the volume of phase space doesn't increase. And it's, and it doesn't increase or decrease. Incidentally, you can imagine laws of physics in which the volume of phase space shrinks. Not too hard to imagine laws of physics where a blob in phase space would be allowed to shrink. It's not allowable in standard classical mechanics. But we could imagine differential equations which sort of push things together. That would correspond to the Lyapunov coefficient being negative and things sort of coming together. That would violate the second law of thermodynamics. In a world like that, the second law of thermodynamics would not be true. It's not a law which is true for all possible differential equations. It's a law which is true for those differential equations which result from standard mechanics. You can't imagine systems with negative Lyapunov coefficients.
I'm trying to understand the size of this little coarse-grained parameter in terms of entropy, like BS equals change in energy divided by temperature. That's pretty much a fixed formula. You said a moment ago that it's not very sensitive to the size of that. You have two objects and different temperatures, you put them together and they reach the same temperature, so the entropy goes up. How does the size of that little fine grain come into play there? Is that too complicated?
It does a little bit in the formula for entropy. Actually, it's an additive constant. It's an additive constant. You know what it's connected to? It's connected to the same issue of replacing integrals by sums. And replacing the integral by the sum, at worst, adds a constant to the entropy.
So when we talked last week about the entropy of a black hole, we're talking about a coarse-grained entropy?
Mm-hmm. Yeah, absolutely. absolutely. Yeah, and in fact, in all of statistical mechanics and in thermodynamics, the entropy that's being talked about is coarse-grained. In information theory, one sometimes speaks about the fine-grained entropy, but in statistical mechanics and thermodynamics, entropy means coarse-grained entropy. Right? So it means the coarse-grained or logarithm of the coarse-grained volume in phase space. Okay, this is a deep and profound point that puzzled people for many years, and I think it's more or less resolved. This behavior, this chaotic behavior, I'm not exactly sure what the difference is between something called mixing and something called and what's called chaos. Mixing, I think, is the idea that this branched tentacle structure covers the whole phase space pretty uniformly. Chaos is a little bit weaker, I think. I think it just says that the trajectories separate. This, I think, is called mixing. But they're closely related, and I'm not sure if there is a difference between them or not. I've never been clear about that. What the difference between mixing and chaos is, if any.
Going briefly into temporal quantum mechanics, wouldn't the parameters of quantum mechanics give a definition of the degree of coarse graininess?
Yeah, Planck's constant. Yeah, sure. Planck's constant. You can't make it smaller than Planck's constant, absolutely. But the reason that I say that, yeah, you see, if you replace the sum by the integral, well, that's this h bar to a power here, h bar to the n. That's the little cell in phase space, What happens if you multiply the integral by the partition function by a small cell size? Well, all it does is add a constant to the logarithm of the partition function. I just multiply the partition function by this coarse graining here, which just replaces d3px by, it's this business of the difference between the sum times the volume element and the integral itself. That's just a numerical constant in the entropy and doesn't affect anything very significant in the thermodynamics.
But wouldn't you need to factor for the uncertainty principle in the...
You need, the only thing you really, well, okay, in quantum mechanics, when you're thinking about real quantum mechanics, yeah, this thing does matter. But in discussing the classical limit of quantum mechanics, in the classical limit, this just factors out as an all-over multiplicative factor in the partition function, approximately. To the extent that you can replace sums by integrals, this just factors out as a multiplicative constant. And when you take the logarithm, it's just an additive constant in the free energy and in the entropy. Okay, so it's not a significant thing. No other questions about the second law? Okay, that's. All right, we have 20 minutes. Let's do some, is that right? Yeah, that's the correct time. We have 20 minutes, and in the 20 minutes, I want to start we actually did some quantum statistical mechanics, didn't we? We did the problem of the rotor and quantized the angular momentum. That had to do with this funny paradox about complex or structured molecules, why the structure disappears at low temperature, why you don't have the equipartition of energy distributed among all the various modes of motion of a molecule, why you can pretend molecules are point molecules. I want to do another example of it. And this example has many, many applications. It is nothing but the harmonic oscillator. We didn't do this, did we? We didn't do the quantum oscillator. In fact, I don't even think we did the classical oscillator. Okay, let's suppose that a molecule has the structure of a harmonic oscillator. In other words, the internal degrees of freedom are described by an oscillation of some kind. Not the overall motion of the molecule. The overall motion of the molecule, its center of mass motion, it still moves exactly as it did in the point molecule case. But the internal structure of the molecule is just described by an oscillation. We haven't done that yet. Again, we can start classical and see how much energy we expect to be stored in the oscillations. So let's do that. Let's take the case of, now this is a fictitious molecule, and the fictitious molecule is just 2 points on a spring, described by a Hamiltonian or an energy function, which is just p squared over twice some mass parameter. It's not the overall mass of the molecule. It might be some, what's it called, the relative mass, reduced mass. It could be the reduced mass of the two particles. And it oscillates about its center of mass. But whatever it does, this is the kinetic energy of the motion of the molecule. And then there's a potential energy. And the potential energy is the amount by which the molecule is stretched. It's proportional to some spring constant, which we call k squared, x squared, where x is not the position, k squared x squared over 2, x is not the position of the center of mass of the molecule. It's just the coordinate which describes the oscillations. So let us not confuse it. I could have given it different names, but I don't have, I'd rather just call it p squared plus x squared. K, sorry, K. Thank you. K. K. So this molecule is now an oscillator. Then the limit that K becomes very large, that's the limit of an extremely stiff spring. It becomes prohibitively expensive to stretch the string by the spring by any finite amount. So you might expect that in that limit, when K becomes enormously large, that the molecule will behave like a point molecule. It'll become exceedingly difficult to excite any significant amount of vibration because the spring constant is so large. And that should be right. I mean, if anything is right about molecular physics, then that should be right, that that internal structure should be frozen out at very low temperatures in particular. All right, let's just imagine now the statistical mechanics of a single harmonic oscillator in thermal equilibrium. Let's focus on just one molecule, and let's forget the center of mass motion. That we know how to deal with. That's just the usual description of the molecular motion. Let's just focus on the internal vibrations of the molecule. And to do that, we just think of the molecule or its internal motions as a system in thermal equilibrium with everything else, and the probability distribution for the p's and the x's is just governed again by the Maxwell-Boltzmann distribution. Now just a single molecule, a single x and a single p, and the partition function for that single molecule is just the integral dx dp e to the minus beta, where beta is inverse temperature as always, times p squared over 2m plus kx squared over 2. Now, before I go and calculate this, let me just point out one connection. What's the frequency of this harmonic oscillator? The frequency of vibration, omega. Square root of k over m. You can do that by solving Newton's equations. Newton's equations are F equals ma. The force is kx, mass times x double dot. And you can see that the important quantity is k over m by dividing by m. That's the frequency. K over m, square root of k over m is the frequency. All right, so let's keep track of that. Frequency of the oscillator omega equals square root of k over m. Now, here's the partition function. It's easy to compute. We've done this sort of thing before. The two integrations, notice that in the exponent, the p squares and the x squares add. That means that this factor is a product. It's a product of e to the minus beta p squared over 2m, e to the minus beta k x squared over 2. And the integrals also, the integral is also a factorized structure, dx and dp. So dp, integral dx. Just two separate factorized integrals. Right? We know how to do this integral. We've done this integral before. Anybody remember what it is? Just a p integration? Well, it's not quite the square root of pi. It's the square root of pi times 2m, 2 pi m over beta. Right? That's what this integral is. You have to change variables to get 2 pi, to change variables so that this is just e to the minus x squared, or e to the minus something squared. We've done that integral, and it's just the square root of 2m pi divided by beta. The important thing here is the beta dependence, but let's track the whole thing. Now what about this integral? This integral is exactly the same kind of integral, except instead of integrating over p, we're integrating over x. Well, x is just an integration variable. That doesn't matter. And the only difference is that whereas you had a mass in the denominator here, you have a spring constant in the numerator here. So I can immediately read off that the answer is 2 pi, and instead of m in the numerator, we'll have k in the denominator. And that's it. That's the partition function for one harmonic oscillator. And that altogether is equal to 2 pi over beta times square root of m over k. But that's just 1 over omega. That's the partition function, really easy. Classical partition function. What's its logarithm? Log of z is equal to log of 2 pi over omega. Those are constants. Omega is a fixed constant plus or minus log beta. What is the energy? Oh, incidentally, minus log of z, which is the thing that we differentiate. What is the average energy of the oscillator? It's the derivative of minus log z with respect to beta. That's just 1 over beta. So the energy of this oscillator is just 1 over beta, which is just the temperature. Not a half the temperature, not 3/2 the temperature, but just the temperature. The reason it's 1 times the temperature and not a half times the temperature is because there are two integrals here. You get 2 factors of the square root of beta in the denominator, and that gives you temperature for the energy. Notice that it doesn't depend on the spring constant. The partition function depends on the spring constant through omega here. Incidentally, very, very large spring constant means very large omega, very large frequency, very rapid vibration. On the other hand, no matter how large omega gets, the energy stored in that oscillator is always just T. So again, we have the same paradox again, that no matter how stiff we make the molecular bonds, this harmonic oscillator molecule always stores this much energy in the internal vibrations, and there does not seem to be a limit in which it goes over to the point molecule. The point molecule would be the situation where the internal energy was just 0. You might have expected that when the spring becomes so stiff that the molecule would behave as a point molecule, and then there would be no internal energy. There would still be the energy of translation, but no energy of vibration. So again, the same paradox as with respect to the rotational motion of an oscillator. The solution, and there's a paradox. I mean, molecules at low temperature do behave like point molecules. Okay, at low enough temperatures, they do behave. And this doesn't say only at high temperatures. It's at every temperature there's this much energy. But in fact, it's not true. The solution is, again, quantum mechanics. And so in order to understand it, we have to think about the quantum mechanics of the harmonic oscillator. Now, the quantum mechanics of the harmonic oscillator may or may not be known to you in detail, but I think almost everybody, at least in this class, knows the result. And the result is that the energy levels, and this is all we need, that the energy levels are discrete, and the nth energy level is n now is an integer, times h bar times omega. Did I leave anything out? The zero energy. But it doesn't make any difference because adding a constant to the energy doesn't affect anything in statistical mechanics. You can check that yourself. Adding a constant would affect no observable quantity. Of course, it would affect the energy per, it would affect the energy, but that's only because you added a constant to the energy. So it will shift all energies by that same constant. All right, so that's good enough. That's good enough for our purposes. And now we can calculate the partition function of the quantum oscillator. I think we can do it in 10 minutes. Z is now not an integral, but it's a sum. And it's a sum over n, all the energy levels, of e to the minus beta times the energy, h bar omega times n. All right, so for example, what is this? This is 1, that's n equals 0. The first excited level plus e to the minus beta h bar omega. The next level plus e to the minus twice beta h bar omega, but I'm going to write that as e to the minus beta h bar omega squared. And then plus the same thing cubed, and so forth. That's what this n does here. And so the partition function is just this infinite sum. The infinite sum this time, unlike the rotor case, where what was up here involved n squared, that was not so much fun, didn't know how to sum it up. Here we know how to sum it up. This is a geometric series. 1 plus a constant plus the constant squared plus the constant cubed, and it all adds up to, let's put it over here, 1 divided by 1 minus e to the minus beta h bar omega. That's Z.
That's the oscillator part. It's still the pendulum.
This is just the oscillator. Just the oscillator.
There's the other 2 pi h of
Here again.
the 2 pi m over beta is the other part.
2 pi m. No, this is the full harmonic oscillator. This is the harmonic oscillator, classical harmonic oscillator. This is the quantum harmonic oscillator.
But doesn't it have, didn't one of those things come from the p squared over 2m?
No. The p squared over 2m plus the kx squared over 2 is what's quantized.
Oh, okay.
Right. It's the sum of these two which are quantized. Remember, this is not the overall translational motion. No, it's the sum of them which comes in discrete levels. Okay? It is the full energy of the oscillator. The oscillator vibrates in discrete, right? Good? Yeah, okay. All right, so here's the partition function. That's it. It took 2 minutes to do. And now we can calculate the average energy and see what the average energy of the quantum oscillator does at low temperature and at high temperature, and see exactly what it does. All right, so what do we want to do? We want to calculate logarithm of z, or minus the logarithm of z to be precise. That's what we're interested in. And that's equal to the logarithm of 1 minus e to the minus beta h bar omega. The minus sign came because this thing is in the denominator, and logarithm of a denominator involves a negative sign. Okay, who's strong enough to differentiate this with respect to beta? All right, I am. Superhero will now differentiate. Okay, first of all, logarithm gives you 1 over the argument, 1 over the thing in the logarithm. 1 minus e to the minus beta h bar omega. Now we have to differentiate the thing inside here. All right? The beta, that means differentiate the exponential here. There's a minus sign from here. And now we have to differentiate the exponential with respect to beta. That's going to give us another minus sign. So it'll become plus. And then just h bar omega e to the minus beta h bar omega. We differentiate it with respect to beta, which gives us the exponential back, but then h bar omega from differentiating, you see what it is. Right? That's the formula. This is the energy of the harmonic oscillator in thermal equilibrium at temperature 1 over beta. It is not exactly, it's not in general equal to the temperature being 1 over beta, not at all that. But let's look at it at different limits. Let's first look at it in the limit of high temperature. In the limit of high temperature, we expect classical physics. Why do we expect classical physics at high temperature? The reason is that at high temperature, this tiny little unit of energy that's in the oscillator is irrelevant. The oscillator is excited to such high energy that it doesn't give a damn that the energy is quantized in these tiny, tiny little steps. So we expect the classical answer for high temperature. Okay, let's look at it for high temperature. High temperature means small beta. Okay, did I get this right? Yeah. Okay? No beta in the numerator. No beta. Incidentally, I can write this a little neater. Multiply the top and the bottom by e to the plus beta h omega. That'll turn into something a little bit simpler. H bar omega. If I multiply by e to the plus beta, this one will go away, and I'll get e to the beta h bar omega minus 1. That's a little neater. Yeah, plus. Okay, let's look at it at very high temperature. High temperature means small beta. Small beta, we expand the exponential. We have a small number here, and what's the expansion of e to the beta h bar omega? E to the beta h bar omega is equal to 1 plus beta h bar omega plus higher order stuff. Plus higher order. All right, the only reason I have to keep the first correction here is because the 1 cancels. Okay, so the 1 cancels, and after the 1 is canceled, this is just h bar omega divided by beta h bar omega. The h bar omegas cancel, and 1 over beta is temperature. So at high temperatures, when beta is small, we just reproduce the classical behavior. So when the temperature is high enough to be able to excite the discrete vibrations of the harmonic oscillator, we reproduce this situation where the oscillator has temperature T. But what about low temperatures? At low temperatures, beta is very large. E to the beta h omega is very large in general. The 1 can be ignored in that limit. This is now low temperatures. And you can see that the energy in the oscillator is exponentially small. Beta is very large at low temperature. This exponential here is very large. And the energy in the oscillator is very, very small, exponentially small. All right, so the oscillator at low temperatures is frozen out. It's frozen out by quantum mechanics. The h bar omega in the numerator is insignificant by comparison with the exponential in the denominator. Exponentially small energy. And so the internal vibrations, as I said, are frozen out. Is there anything else worth saying about this at the moment? Well, that is the important thing. Oh, yeah, one other point. Where is the crossover? At high temperatures, it's T. At low temperatures, it's this exponentially small thing. Where does it go? So let's see, what does it look like? At small temperatures, as a function of temperature, let's say, this is extremely small, and it goes to 0 very, very quickly at small temperatures. Okay? And then, at some point, it takes off and it goes linearly, like this, with temperature. Somewhere in here, there's a transition. It's not a sharp transition. It's a sort of spread out from exponential behavior to linear. But where does it occur? It occurs when the exponential behavior, when this exponent gets to be about of order 1. Somewhere in the vicinity, when the exponential gets to be of order 1, that's where the transition happens. And that means when beta h bar omega, well, order 1 or order 2 or order 3 or some number, not order 1 because order 1 happens when beta is equal to 0, but at some numerical value of this exponential, it turns over and goes from one thing to another. That means it happens when beta h bar omega is about equal to 1. But what is beta? Beta is 1 over temperature. So what happens when the temperature is about equal to h bar omega? In other words, when the temperature is high enough that the classical approximation would allow the system to have 1 quantum's worth of energy. Below that temperature, the oscillator is frozen. Above that temperature, it doesn't realize that it's not a classical harmonic oscillator, and somewhere in between the transition happens. So that's what tells you at what temperature the transition between quantum mechanics and classical mechanics happen. The lower the frequency of the oscillator, the lower the temperature at which the transition takes place. So if you have a very floppy oscillator with a very, very small frequency, then at low temperatures, it starts to get excited. The transition happens at the... On the other hand, if you have an extremely stiff oscillator, it takes a high temperature before it starts to behave classically. All right, that's the basic theory of the harmonic oscillator, and it governs just about every system in nature that we can solve. But in particular, it governs black body radiation. So next time we'll talk a little bit about black body radiation and get more confusion about integrals again, I'm sure, because we'll discuss black body radiation. Good.
For more, please visit us at stanford.edu.